In 1982, around 300,000 students all around America took the SAT test. There was nothing special about that test because it happens regularly. But there was one single math problem stood out. Because out of all these 300,000 students, not a single person got it right. Here's that question. The radius of circle A is 1/3 of the radius of circle B. Starting from the position shown in the figure, circle A rolls around the circle B. Assuming circle A doesn't slip while rolling around the circle B. Now, how many revolutions would it take for the center of circle A to first reach its starting point? You can pause this video to think about your answer for a second. You have your answer now? Okay, I also need to tell you what I told you was not the entire question. This is a single select question, and here are the options. 3/2, 3, 6, 9/2, 9. So which one did you choose? It should be very easy and straightforward. We can simply apply the equation for calculating the circumference of a circle, 2 times pi times the radius of the circle, and get the answer, which is B. End of story. But how come not a single person got it right? It's very strange because if you really think about it, even if nobody knew the right answer, and everybody just randomly picked one option and submit it, the chance of at least one person to get it right would be very decent. So what went wrong? Well, it turns out the right answer is not in these options, which means whoever put this question in the exam, they were confused too. To get to the right answer, we need to use a real-life example to demonstrate it. Intuitively, it makes total sense to apply the circumference equation to this problem. If you turn the big circle into a straight line, and you roll a small circle along this straight line, it would take exactly 3 revolutions for the small circle to get from one end to the other end. Now, if you turn the straight line into the big circle, that end point of the small circle is exactly its starting point. However, if you roll the small circle around the big circle, even though the circumference of the big circle is exactly the same as the straight line, the game changes. Now, it would take 4 revolutions for the small circle to go around the big circle. What? Where did the extra distance come from? The best way to understand it is to understand how we normally think. But before we go any further, let me ask you an opposite question. Given exactly the same circumstance, how many revolutions would it take for the big circle to go around the small circle? You can pause the video and think about it for a second. Do you have your answer now? Good. Now, every time when we observe or think about a circle that it travels along a straight line, we normally intuitively would find one point on the circle and use that as a reference. We would then use this point to track how many times the circle has revolved. When the point touches the straight line again, the circle has revolved for exactly 1 time. And the distance the circle has traveled is equivalent to its own circumference, which is also the distance the center of the circle has traveled. It would be very helpful to think of it backwards. Whenever the center of the circle has traveled for its own circumference, the circle will revolve for exactly once. If you use this perspective to look at the 2 original circles, something might appear. You might be able to see that the small circle is actually traveling along an invisible circle, whose radius is 4 times to its own radius. And now, if we apply the circumference equation to this problem, it would prove the observation we had earlier, which is that the small circle would revolve around the big circle for 4 times. It would also give us the answer to the opposite question, which is that the big circle would have to revolve around the small circle for 4/3 times. one question left, which is that when the straight line turned into a circle, where did the extra distance come from? You can see from this simulation, there was actually no extra distance created. When the straight line turned into a circle, the time it takes for a certain point on the small circle to touch the big circle again is asynchronized to the time it takes for the small circle to revolve once. It was exactly this subtle detail that tricked most of us. I find this question fascinating because it's very simple and yet it's very counterintuitive. By simply turning a straight line into a circle, what was synchronized all of a sudden becomes asynchronized. And that's where it tricks us. It also reminds me of another question. If you roll two circles with different sizes along a straight line for one revolution, the big circle would go much further than the small circle. However, if you pin the centers of these two circles to the same point and roll the combined circle along a straight line for one revolution, all of a sudden, the small circle would go just as far as the big circle. So what is going on? What happened? Is the small circle rolling faster? How would you explain this?